You didn't like. You didn't like. No, yeah. So, all right.
Whatever. He has 2 daughters. He knows what TikTok is.
So,
Daughters? Yes.
I'm partially correct.
Welcome.
I'm
pretty sure my parents built their house.
It's like it's like
like
middle school, like down.
all right.
It's on like Mongan Road. That's not it.
Let's get started here. So, for number 5, I'm going to cover how do you use these derivative rules to like analyze a piecewise function, and then we'll go over second derivatives, which is like pretty easy. So when we looked at these before, all we could do before was basically draw a picture of the graph. So this graph would be a shifted up parabola. There's 1. So this is 2. And then a line 3 minus x. What's the y value at the junction here? So here you get 2. You plug in 1 here, you get 2. You plug in 1 here, you get 2 again. So what does that mean?
Connected.
They're connected, so they're continuous. So you'd say this is a continuous everywhere function. Is it differentiable everywhere?
No.
No, clearly not. Clearly there's a pointy there. Okay. And so let's actually look at the derivative. You're gonna like this because it actually makes a lot of sense. It makes intuitive sense, I think. The derivative of this would just be take the derivative of each piece, because like look at the left half of it. It's a parabola. I mean, we know how to take the derivative of a parabola, right? So what's the derivative of this piece here? 2x. So that's the derivative as long as x is less than 1. Everyone cool with that? And then what's the derivative of this? -1. I'm going to put a mistake on this. Where's the mistake?
Is it the equal to?
Yeah, that. Yeah. This would suggest that I can plug 1 in here and f prime of 1 exists, but we know that f prime of 1 doesn't exist. It's not differentiable. So you actually, no matter what, this function can't be defined at 1. So that's an easy way to do that, is you just say, here's what the function is when x is less than 1, here's what the function is when x is greater than 1, and then it's just implied that if x is 1, it's undefined. So then let's graph that. Here's 1. So it goes from 2x. It's kind of coincidentally, it ends up being equal to 2 there, but that's just a coincidence. The fact that it's the same y value. It's just a coincidence. And then it goes down to -1. Where's George today? He's
Uh-oh.
breath. Okay, so there's I asked you here to write a statement about how the continuity of the derivative graph was affected by the behavior of the functions graph. So all that means is a short little, like, not even a full sentence necessarily, but you can make it a full sentence if you want. It would just be something like the pointy at the x value of 1 on the graph of y equals f of x caused a jump on the graph y equals f prime of x. Sorry, this marker's not very good. Hopefully that's legible. Seems borderline. This says that the pointy, or I can say sharp turn also, the pointy spot at 1, right, on the original graph, the graph of y equals f of x, translates into a jump discontinuity on the graph of f prime. Does that make sense to everyone, what I'm talking about? So, let's do another one. Let's look at, maybe let's do this whole page together, because then you can do 6 on your own. But these have very different, but like it's kind of a nuanced thing. You have to be very precise if you really want to understand what's going on here. So why don't I set up B while I'm erasing here? Take the derivative, see how good of a graph you can draw. I think I might rewrite this one. How would I want to rewrite this to make my life easier? Yeah, so it's 6 times x to the 1/2 power. So remember, I always want it to be in the form of, just write a little reminder over here in red. I always want to be doing the derivative of some constant times x to some number. The derivative is going to be a times n times x to the n minus 1. So, okay, let's let's draw the graph first, actually. Graph first. All right, so the switch happens at 1. There's 1. What's going to happen on this graph? It's going to be a jump, right? So we got this graph, so here's 1. Now I'm not going to draw it to scale, but there's going to be a 6 up there. So there's my cubic function stopping at 1. And then I got to do a square root function that I got to pretend like it started down here and just kind of continue it. So it's going to look something like that. Close enough for government work, as Michael J. Knudsen would say. Does he still say that?
Yep.
Yes, he does.
What a legend. What a legend. Okay, so derivative time. This derivative is a little bit harder than the last one. So the derivative of x cubed, is 3x squared. So that's my derivative when x is less than 1. And then this guy is going to give me 3 times x to the negative 1/2 power. Now, can the derivative exist at a jump?
No.
No. Remember, discontinuity implies non-differentiability. It's a fancy sentence. Discontinuity implies non-differentiability. That'd be a great senior quote, by the way. Not saying you have to. I'm just throwing it out there. That'd be a really good one, I think. I would definitely, I got my yearbook and I'd be like,
My senior goal is definitely going to be big.
oh, God. I will take an X-Acto knife and then cut your picture out of the yearbook. No, I'll just take a Sharpie and write out Big Blue Moon. I'll keep your picture in there, but that's triggering. It's very triggering. Okay, so now this here. That would ruin me. This, you're probably going to want to write this as 3 over root x.
No, you guys are like getting intermediate.
I don't know if you agree with me here, but I think this is a lot easier to look at and just kind of get the end behavior and stuff just by looking at it than this. But they're both equivalent. You just got to know that they're equivalent. Okay, so what does this graph look like?
Excuse me.
There's a parabola, a parabola.
Thank you. I don't know what you're saying. No, thanks. I appreciate you.
Oh, what the blessings. Stop being
What?
Big blue one. Okay, so there's the left half. And then this, what does that look like?
Upside down.
Buy it. Oh, precisely, yeah. So it looks, that by itself looks like that. If we cut it off at 1, what's the y value though? This is the really interesting part of this connection here.
It's 3, but.
They should both have a y value of 3, but we also know that this function's not differentiable at 1. So they're gonna sort of connect, but there's a hole there. So this one, actually articulating the connection here is a little bit challenging because you have to, because this could have very well been just a jump in the graph. So how come it's a hole and not a jump?
Great.
No, come on. I bet someone can. If I draw that, maybe I should draw this picture a little bit better. I didn't draw if I draw a really good picture, it might be able to be clearer.
Oh, because it's almost like.
No one thinks they got a good. The question is, how come this jump? Well, let me clarify something. Will a jump always lead to a hole? The answer, of course, is no.
No.
No, it won't. But in this particular case, it just happened to be the case. So the question is, why does this particular function's jump end up giving us a hole on this graph? Anyone think I got to take a shot at that?
Is it because they're both 3x?
Yeah, it has to do with the fact that, like look at this, they both. What's the slope of this, roughly speaking, what's the slope of this graph just before the breaking point?
very,
It's very
nicely.
positive.
Oh, through this curve.
Right, so just before we get to 1, as we approach 1, what's the slopes? About 3. Because if I plug 1 in here, I get 3. What's the slope of this part of the graph just to the right of 1? Just really close to 3. So what's happening here is that the tangent lines here are very close to a slope of 3, and so are these. So yeah, it's non-differentiable at 1, but just to the left of 1 and just to the right of 1, the slopes are very close to 3. So that's why over here, the graph is approaching 3. Is that confusing or?
Is that something that we absolutely need to know?
Well, nothing is that.
I mean,
What a great answer.
like, is it gonna be on a test?
That exact question? I don't know. Yeah, I'd say that this is pretty fundamental to understanding what we're
No,
doing.
I mean that, what you just asked, like why?
Yes, understanding the connection between a function, a graph, and its derivative is pretty fundamental. Yeah, it's pretty essential. Yes, Caleb?
So if that was shifted down like 5 units, would it then be differentiable?
Yeah, that's a great point. If this was shifted down, so if we made this 6 root x minus 5, and they actually connected, then it would be a smooth continuous function and differentiable there, and then this graph would be continuous. You'd have it filled in. Okay.
Neato.
Okay, so let's look at. We can do C, sure. Oh, so sorry, the sentence here would be something like. Here, I'll write it down here. So, to be precise and explain that connection, you'd say something like, the jump at x equals 1 on the original function caused a hole let's see, how should we phrase this? Because, so why was it a hole and not a jump? Well, because we can make some really precise math statement about how, actually, no, that's good. That's good for you. That'll enrich you. Here, tell me if this statement makes sense, guys.
Oh, yeah, that makes sense.
Okay. So, I don't know how many of you guys are planning to take the AP test, but this is the kind of stuff they a lot of times are looking to see is these kind of, or the kind of statements they'll throw at you and see if you can understand them. So this says that if we are examining the limits, the derivatives of f, if we're looking at the slopes, approaching from the left and from the right, on both sides, those slopes are approaching 3 as our x values approach 1. But actually at 1, the derivative doesn't exist. Does that make sense, everyone? If not, you could write this statement and think about it some more, and then it will make sense. It might take some more time to let it sink in. Okay. Okay, let's do C. I was thinking because statements like this, these really precise statements, most of the time they don't make sense the first time you see them. You gotta think about them a little bit. Okay. This is gonna be kind of boring.
Can you do 6A instead of 5?
Yeah, I mean, you guys know this is a lot like A. The only difference between this one and A is that this guy's an asymptote. So yeah, of course, at the asymptote, there's going to be an asymptote on the derivative. But 6A.
I just have a question on the clarification of it.
Yeah, so on 6A, so we can do 6A. So this one, guys, so there's a little hint for you on 5C. It's going to be very, very close to 5A. There's going to be a sharp turn in there. It's continuous, but it's going to be a sharp turn. So you'll see a jump in the derivative, but you're also going to see an asymptote in the derivative because the function has an asymptote. Okay. All right. So I agree. Great. This one's a bit more demonstrative, I think. Demonstrates an idea. Okay. So look at this graph.
Look at it.
Is that a meme? Look at this graph. Yeah, I remember now. I didn't mean to
That's
make
more
a
of
meme.
a vine than a meme.
I'm sorry. Okay, so what does this look like?
Educate yourself.
Y equals X all the way up till you hit 0, and then switch over to a square root function when you hit 0. So that's what the graph looks like. Is this graph continuous everywhere? Yeah. So let's see what happens on the derivative. Okay, this one's pretty easy, right? What's the derivative of that? 1. And then derivative of this one, by the way, this one comes up so much, guys. I mean, most students typically memorize this result. The fact that x to the 1/2, okay, becomes 1/2 x to the negative 1/2. So another way to summarize that is that the square root of x derivative is 1/2 root x. So that result is such a common result that it's a good one just to kind of like know. So 1/2 root x when x is greater than 0. Now, think about that. It's a little weird.
Now.
Well,
There's a vertical.
very good. There's a vertical
You
asymptote now.
okay?
Okay. So what happens here is you got a vertical asymptote. Well, let's get the left half first. That's the easy part. Y equals 1 until you hit 0. That's pretty easy to graph. But then this, for any positive x value, it's this. And we know what that graph looks like. It's like that. So there you go.
So on the statement we're making, is that considered an asymptote or?
Right. So let's think about what makes this non-differentiable. So this is something we haven't talked about much yet. We've touched on it a little bit, but so what does this kind of imply about the slope?
It's very,
So
very, very.
It is pointy, but if you want to talk about limits of the derivative, like as we approach from the left, our slopes are all 1. As we approach from the right, our slopes approach infinity. So we call this here is a vertical tangent line. Well, let's think about that for a second.
It makes sense because it's approaching the vertical.
Yeah, so you might recall back to like way back, algebra 1,
Way back
when you're talking about slops, right? What's the slop of a vertical line? Undefined, right? Because if you do rise, so take a vertical line, and okay, here's a point, here's a point. Let's do rise over run. So let's say the rise was 4 and the run was 0, that's undefined. Okay, so if you're analyzing a function and the function has a spot where the tangent line would have to be vertical, then the derivative, remember derivatives are tangent line slopes, right? So if the tangent line has an undefined slope, then the derivative is undefined. You understand that?
Mm-hmm.
Okay, so there's a few functions out there. It's actually, the problems where I ask you about this are a little bit down the road here, I think. So it's number 23. So we're getting a little ahead of ourselves here slightly, but if you think about, like, say, a cubic function, cube root function. You know, we've taken this derivative, and you probably notice that when you look at cube root function, the derivative doesn't exist at 0 because you end up with a 0 in the bottom of the fraction. That's because this tangent line here is vertical. Have I confused you? Are you confused? Let me go over that. Okay.
Statement.
What?
What was the statement?
For this one?
Yes.
The vertical tangent line on the original graph caused an asymptote on the derivative. All right, let's talk about second derivatives a bit. So now you got to do 3 on your own. Hopefully that'll be enough for you to see if you understand the idea. We can check 1 or 2 of them tomorrow if you'd like. As always, I'd encourage you to try a question and then compare with a classmate. You'll learn a lot more that way than just listening to me tell you the answer. Okay, there's a couple second derivatives on here. There's only 6 because it's a pretty straightforward idea. And there's not really a need to practice it a million times. Who wants to take a shot in the dark as to how do you find a second derivative of something? Yeah. You take the derivative and you take the derivative again. That's all you do. So I'll do a really simple example just to illustrate the point. Let's say now the notation is I showed you a bunch of different notations on this page. This is one of them. This would say take the second, what? Yeah, or f prime prime. So this is one way to write it. This is kind of like going like this, d over dx of whatever, some function. You can see why you get d squared over dx squared.
Yes.
Yes, okay. So a really simple example of that would just be, let me pick a function like, whatever, 3x to the
Square.
fourth or something, whatever. Like, so what you do is you go 3x to the fourth. The first derivative is 12x cubed. The second derivative is 36x squared. That's literally all there is to it. Make sense?
Yeah.
Okay, so this first one's 7A, sorry. All you gotta do, so yes, please show this step, the first derivative. The first derivative is 15x squared minus 8x minus 1. That's the first derivative. The second derivative, or f double prime, that's how you say that, double prime. F double prime would be 30x minus 8 minus nothing. So there's your answer. Not too painful, right? Yes.
Like a shot in the dark, are we like, is something in the future we do is like, you're just gonna keep on doing derivatives, so you only have like one X value left?
You could, yeah.
Is that like an actual thing?
Yeah, some functions, that's an interesting question. I mean, so yeah, you could take a function like, sure, take x to the fifth. You'd go 5x to the fourth, 20x cubed, 60x squared, 120x, 120. So any polynomial is going to eventually get down to 0. But there's some functions out there. I'll show you. Here's a meme one for you. Remember this function, Winslow? E to the x?
Yes.
It's the derivative of e to the x's. It's a very special function. It's e to the x. Yeah. That's what makes him so special. He's the only function out there, except for y equals 0, I guess, who's equal to his own derivative. So yeah, what a legend. What a legend. So this guy would just be that forever. Now other functions, maybe you can make another weird function, like you could say, here's one like e to the 2x. Turns out his derivative would be 2e to the 2x. And his derivative would be 4e to the 2x. And then 8e to the 2x. So some functions out there, you can differentiate them infinitely forever. Some functions you'll eventually get to 0. You know.
So Daniel, what are you using derivatives for in actual, like, real life executions? Well, yeah, in
Lots of
engineering,
stuff.
but like an example, I guess, of
Well, it was
how it would
invented,
be used.
Newton invented it to give he invented calculus in general to describe orbital mechanics. So we had all this, we had observed all this planetary, like celestial motion for a long time, and we had various models. If you look up Ptolemy's model, it's very interesting. It's extremely convoluted, but it was very accurate. Like it actually described the empirical evidence very accurately. But it's crazy. If you look it up, it's all these like little epicycles and, anyway, they built the physical models of it. Anyway, so he used his to describe planetary motion. So anything in physics, really. But here's the simplest example is this. It's, say you have position. This is going to be one of our problem sets. But so if you have position, a position function of something, like, hey, I got this function that tells me where something is at different times. The derivative of position would be velocity. So this was, so let's say something was moving along, say, the y-axis. So here's a particle, right? Here's a particle. And he moves along this y-axis. So his position function would be a y function. His velocity would be a y prime. What's the derivative of velocity? Acceleration. It's all rates of change. Guess what the next one is? Jerk. And then there's snap, crackle, and pop. Yeah.
Yeah.
These were just a joke after, not my joke, but like this actually is a thing, but I think the people that coined it were like, this they came up with, because it kind of made sense, kind of went with these, and then they were like, oh, I'll get it. But apparently I've read that like this you can feel on a roller coaster very easily. This is a sensation you like, if you're designing, let's say, a ride at an amusement park, you'd be very concerned with this because your riders are not going to be like very comfortable if they're experiencing.
That's just the change in acceleration.
Yeah, so like, yeah, so if you like when you're dropped, you're experiencing a constant acceleration. So if you drop something, the whole time you're falling at you're speeding up. You're gaining 9.8 meters per second of speed every second if you're falling. That's constant acceleration. Now, if that acceleration itself is changing as you move, that's jerk. Okay, and so you can sense that. What I've read though is that these are used a lot, not a lot, but like you have to take into account if you're say like developing either a simulation or something that's supposed to mimic like animal movement. You ever notice that like it's really hard? Animators have had a hard time getting like say, oh, I got this like cartoon deer running, and it always looks kind of weird. You can just tell from looking at it that doesn't look right. You know what I'm talking about? Especially human movement. Like if you wanted to make a simulation of some person, facial movements, hand movements, arm movements. This kind of stuff then comes into play because the brain can somehow pick up on that stuff and just, you get into the uncanny valley. Yeah, we talked about that one, uncanny valley. Another good example, a really simple, kind of more boilerplate example is stuff like maximization. Where like, here's you own a business. Here's like whatever your revenue over time. You'd be very concerned with derivatives on this because this kind of derivative means you're happy. This kind of derivative means you're not so happy. And then you can talk about stuff like, if you want to say like, here's your profit model, profit versus quantity produced. You want to talk about maximizing. You want to getting into when your derivative changes from negative, changing from gaining profit to losing profit. Anyway, hope that's an adequate answer for you, but
Yes.
we'll be getting into plenty of like examples of applications of this stuff, but those are just a few that come to my mind. So, okay, that's it for. Oh, I guess that's the lecture for today. It's probably almost out of time, aren't we?
Yeah.
Wednesday. Oh, we are. Okay.
I can't get over the fact that I think like a pop would be more than a crackle. Like that's all I can. When I think